Alright, hi everyone, welcome to my YouTube channel, CTF Lecturer. So in this past question of course, we are going to talk about this, which is in two parts. The first part is to discuss the design, simulation and comparison of the performance of three-stage cascade amplifier. Three-stage cascade amplifier. Now, using four configurations. So we are going to use four configurations. I'm going to use four different configurations, but for each of the configuration, first configuration 3-stage, second configuration 3-stage, fourth like that. All configurations are made up of what? Three-stage cascade amplifiers. Okay, so forget about this part, that's another question. So let's handle the first part. So design of three-stage cascade amplifier. So first of all, understand this. We are designing, of course, in writing. We are not like because this is past question now, so I believe in the exam hall, I was not there, but I believe they did not design it in the exam hall. It's just write up, I think so. If they did, wow, that's wonderful. But anyways, so the design of three-stage cascade amplifier. So first thing to understand, when we say three-stage cascade amplifier, a three-stage cascade amplifier is a multi-stage amplifier where multiple amplifier stages are connected in series to increase overall gain. So that means you have something like this. You have one amplifier here, okay, amp. I think I don't need that. This is a three-stage cascade. The cascade means this. The cascade means the output of one stage is the input of the next stage. Okay, this is the input now to it. However, this particular point is the output of first, and that output of first is the input of second. Same thing happened here. Okay, now so that's the picture of it. Okay, that's the picture of it. Now, once you pass a signal through an amplifier, that signal is amplified, it's increased. So let's say you have one signal here and it goes into this amplifier. The output, meaning that signal has been increased. That increased signal, we put it into another amplifier, and of course the output increases the strength of that signal, and that signal we now put it into a third amplifier again and increase it. So what comes out, wow, is really amplified. Okay, so we have more signal strength. Now each stage amplifies the signal progressively. All right, so the components used are transistors, okay, BJT or FET, but in our example here, the one we used in this video is just BJT. So once you see, BJT is a bipolar junction transistor, so, and they have 3 pins: base, emitter and collector. All right, so let me just quickly draw that. So you have it like this. Okay, this is base, and here we have the collector, and here we have the emitter. Okay, so this is bipolar junction transistor. All right, let me add this guy. All right, now okay, so where are we? Okay, so the components used: transistor, BJT or FET. Then we'll now make use of biasing resistors. Okay, don't worry about the name biasing. The biasing is just the way they are connected. Okay, the way they are connected. So the way the system is biased or connected. So transistors, resistors, capacitors, and then a DC power supply. So for the capacitors, we have the ones for coupling, we have the one for bypass. Okay, so if you are asked what are the components used: transistors, resistors, capacitors, DC power supply. Okay, so how we use them? How we use the resistor is for biasing. How we use the capacitor, we use it for coupling. How we use another capacitor, we use them for bypassing, like bypass capacitor. Okay, Then what's the purpose of this system, this network? The purpose of the 3-stage cascade amplifier, the purpose is one, to increase voltage gain. Okay, and when you increase voltage gain, you are actually doing what? Improving your signal strength, and then also to maintain the signal shape. Okay, so from these guys, this example we gave here, of course, improve the voltage, which is actually you are also improving signal strength, but we want to maintain the shape of the signal, while the strength is increased. Okay, so that's the three. Those are the purpose of this thing: increase voltage gain, improve signal strength, and maintain the signal shape. So now let's talk about the 4 configurations. Each of the configuration have 3 stages. 3 stages. Now the first configuration is common emitter. Okay, common emitter stage. Let's just mention all configurations. Just bear common in your head. Okay, just hold common in your head. How many pins do we have? We have base, emitter, and collector. 3 pins. That means we'll now have what? I said put common in your head, right? Put common. Pardon the handwriting. Common. I don't have my pen here with me, so alright. So common collector, common base, common emitter. Exactly. With this idea, you have known all 3, or you can mention all 3 configurations. There's a 4th one. Okay, there's a 4th one. So this is the now common emitter, common collector, common base, and the last one in this video is cascade mix configuration, meaning we mix some of the 3 stages. Look at the 3 stages: 1, 2, 3. One of the stages will be common emitter, common emitter, common emitter, or common emitter, common base. Sorry, I think one should be like collector, should be mixed. Common collector, common emitter, common collector. You see that it's mixed now. So I can even say, let's start with a common base. So when you mix the configuration like this is the cascade mix configuration. But for this one, this one is you have common base. Let me copy it, take it that way. So for this one, you have something like this: common base. Everywhere we just common base configuration. Okay, and then for this other guy to be common collector, common collector, and for this guy it will be common emitter. While for this cascade mix, meaning one will be common base, other will be common emitter, other will be common collector, or common emitter, common base, common collector, or common collector, common emitter, or you understand, mixed. Okay, so this one is used depending on the required performance. All right, then this is the table that helps us simplify or summarize everything. So the performance comparison of the configurations. Here we have configurations: CE, common emitter, common collector, and common base. Here we have the gain. So for common emitter, the gain is high. Gain in the sense that look at, we drew something here now. So we have input. If the output is high, then we say we have more gain. Gain is actually gain. Oh, I need my pen, and my pen is not here. So gain is oh boy. So gain is output over input. So if we're talking about voltage gain, it will be voltage gain will be okay, out over in. Okay, so if the out is very large and the in is small, by the time you do this division, if you have high voltage gain. So that's what we mean by gain right there. So yes, so let's just finish this now. For common emitter, we are told that the gain is high. For common base, the gain is also high. But common collector, the gain is approximately 1. It's almost like your output and input are almost the same. Okay, so the gain is approximately 1. Now, input impedance simply means that resistance to the flow of current in the input part of it. So for the input part of it, the resistance for common emitter is medium. It's not that, yeah, it's just medium. But for common collector, the resistance is very high. Okay, high, not very high. Let me just say high. So the resistance is high. Then for common base, the input impedance is what? Is low. So we can say all three: low, medium, high. Low, medium, high. But for the output impedance, that means for current flowing out of the system or that particular stage or that configuration, the output impedance is what? For common emitter, the output impedance is low. Sorry, it's medium. So then for common collector, the output impedance is low. For common base, the output impedance is high. Now, for this guy having medium impedance, is what? The stability is good. Okay, it's kind of good. But for the common collector that is having high input impedance, resisting how much current flows in. However, the current that flows out, it allows more current to flow out, meaning it's actually stable, very stable. Then for common base that has what? Low input impedance and high output impedance, it is only stable at what? High frequencies. Are we getting it? It's stable at high frequencies. Now, since it's stable at high frequencies, that means it can be used for what? Radio frequency circuits, because radio frequency is actually high frequencies. So common base is applied. The application common base configuration is applied at in where radio for radio frequencies, circuit that has to do with radio frequencies. Then for this guy, which is very stable, and you see that the gain is what? Approximately 1, meaning our input is almost the same as output. So we can use it for what? Buffer stage. Buffer just kind of holds what comes in, and when it's time to give out, it gives out that same, almost same thing. Okay, so buffer stage, because you see that the gain is just approximately 1. Then since this guy, the gain is high and the stability is good, and then we can use it for general applications. General amplifications. Okay, general amplifications. So the parameters that was observed, or that is to be observed if you are to carry out this work, this design, is the voltage gain. I think I've mentioned that in a lot. Voltage gain. And since we talked about stable at high frequencies, we should also talk about bandwidth. Consider bandwidth and phase shift. This thing I mentioned, phase shift. Phase shift in the sense that if you have a signal like this, okay, phase shift meaning the output will now be like this. So this one is inverted 180 degree. Okay, 180 degree. You see that it's just the opposite. This one goes down, this one comes up. Look at it, it's just the opposite. Okay, so we'll consider phase shift. Then distortion, the signal that is amplified, do we have the same shape, or it's being distorted, or the distortion? Okay, something that is not clear, or what you have as input, what we get as output, it doesn't look like the input, and then if what we have as input doesn't look like what we have as outputs, that means our signal has been distorted. Okay, so that's the idea of distortion. Then noise level, and yeah, similar to distortion. So you see that phase shift. Look at it. If we have no phase inversion, meaning the way we have the shape as input, we have exactly the same shape as output. But if we have, that's for common base. But if we have if we have phase inversion 180 degree, that's in common emitter, that means if our input is like this, our output will now be like this. Okay, if our input is now like this, our output will be like this. That's for 180 degree phase shift, and it happens in common emitter. Okay, so I think this is all for this video and design of 3-stage cascade amplifier. So we mentioned that these are the 3 stages: first stage, second stage, and third stage. And then the 4 configurations: we have common common emitter, we have common collector, we have common base, and then we now have the what cascade mix configuration. And we said that these are their comparison. Okay, these are their comparison. Gain, common emitter high, this one is almost 1, this one is also high, and these are their impedance, input impedance, output impedance, and their stability and their application. Okay, so that's it for this video. Like, share, subscribe, comment, and I'll see you in the next one. Bye for now.